Time, such a familiar thing to all of us. We know what we mean when we say, what's tomorrow going to be like, or how was yesterday, or what are you doing at 7:30, or what are you doing tomorrow? These are terms we all understand. It's so familiar to us, and we use clocks. Our entire lives are run by clocks. We use timers, we use alarms. If I told you wait about 10 seconds, you know what that means intuitively. It's very intuitive. But clocks can tell us that time is ticking, but can it measure what time really is, what those ticks really are? What is time? Well, the first notion of time starts with our ancestors. They saw the sun rise and the sun set, and they kind of gauged their day based on the sun's position in the sky. Next were sundials, where now they were able to divide the day into hours. And after that comes pendulum clocks, able to turn those hours into minutes and seconds. The clocks on our wristwatches measure the ticking or the movement of quartz crystals. So what we're really doing by using these clocks are measuring the frequency or the repetitive motions of certain objects. And that's really what our understanding of time is to our brains. This repetitive and even cyclical entity that runs our lives. But it goes deeper than that. The ancient Greeks asked these questions, and they thought time was absolute. They thought that there was a universal clock in the background of the universe that was continuously ticking and ticking and ticking. This thinking was also inherited by Isaac Newton, who also thought that time was absolute and fixed. But then Einstein came along and completely challenged that notion and utterly enriched our understanding of time itself. Einstein thought that instead of viewing the universe as having one time, he could divide the entire universe into sections of time. He found that there's this exchange between space and time. The more you have of space, the less you have of time, and vice versa. Much like you can imagine a two-dimensional diagram, where we have one axis going north and south, and another axis going east and west. The more I move in the direction of east or west, the less I'm moving in the direction of north or south. There's this interesting exchange on this two-dimensional level. And this is how Einstein saw the entire universe. But instead of 2 dimensions, he saw 4 dimensions. 3 spatial dimensions, we call them X, Y, and Z, and 1 of time, or T. And for more about relativity, go check out my recent video called Relativity Explained. You see, what Einstein found in his special theory of relativity was that light moves at a constant rate in a vacuum. It never changes. And for all observers, the speed of light, or c, is the same. And because of this fact, the more you move through space in any spatial dimension, the less you're moving through time. And this isn't just crazy talk. This is something we can actually observe. Scientists took 2 atomic clocks that were synchronized perfectly on the ground. So they took one of those clocks, they put it on a plane, the other clock stayed on the ground. And the one on the plane, as it moved through the air and was traveling at hundreds of miles an hour, it came back, and scientists were able to see a measurable difference in the times of those 2 clocks. The times were different. This is called time dilation. And modern day satellites have to take relativity in consideration when we have these satellites up in orbit. We have to actually compensate the times in the satellites to synchronize with the time on Earth. So it turns out the gravity we experience, the motion through space we experience, directly affects our experience of time. But in our daily lives, time dilation isn't really noticeable. But on huge scales like that of the universe, little changes in our motion or our velocities can have tremendous impacts on how we see the now moment versus somebody else on the other side of the universe. What I consider now is me recording this video, the sound of the fan in my room moving, the sound of my computer, the sound of my heartbeat. These are things I consider them the now moment. It seems that my present is all there is, that the past is gone, that the seconds that have just elapsed are never coming back, and the future is yet to come. We're waiting for the next seconds to occur. But this is challenged by this relativistic understanding of time. So because there is no one now moment in the universe, and in fact, my present can be your future, and your future could be my present. The notion that the future is yet to come and my past is gone is gone out the window. Now all of time must exist. What I call the past and what I call the future all exist simultaneously. And this is another byproduct of relativity called Einstein's block universe. You can imagine the entire universe existing as a block all the time. My past, my future, and the present all exist as a block. It just is. Imagine slicing the entire universe into little individual slices, and each frame of the universe is what I call a now moment. And you can imagine stacking up all these now slices on top of each other, like a big loaf of bread or a big block of cheese. And all time exists simultaneously. Much like a movie. When you put on a movie, the entire movie exists in the cloud or on a disc. All the frames are stacked into one DVD or one movie or one film. That's how the universe may actually exist. Just as we see objects in the universe just being there in space, and all the space around us exists simultaneously, we can view time in that way, and that all of time exists simultaneously. So under this view, time doesn't necessarily pass. Because all of time exists, there actually is no present moment that we're moving out of and into a future moment. All the time just already is. That four-dimensional block could go on forever, in both directions. Perhaps time could be infinite. Time and space may be infinite as an infinite block. So it's not that we're passing or traversing through time to get to this moment. It's that all the time already exists. Now you might be asking, well, why does it feel like we're moving through time then? It feels like we're always moving from the present to the future in one direction. There's a flow of time, much like a river flows in one direction. Now you might be saying, well, there must be some kind of law of physics that describes why there's a flow of time. But there isn't. There is no law of physics that says time must work in one direction. Physics actually allows for time to reverse without any consequences. A scrambled egg could de-scramble itself. A broken wine glass can restructure itself. And there's nothing in the laws of physics that disallows this, because all you're doing is reversing all the velocities, which incorporate time. As long as you reverse all the velocities and all the directions and all the times, you can actually reverse time with no consequences. So there's nothing in the laws of physics that says you must travel in one direction. So why does it seem we're traveling in one direction then? Well, just like before we said we can treat time like space, in space there is no one direction of space. In space, if I'm an astronaut, there is no sense of up or down. I'm just in space, and every direction is treated equally. But on the Earth, there is this sense of up and down, right? If I threw a ball in the air, I can understand intuitively that it would fall down. The reason why is because of gravity. Gravity is giving us the sense that there's a direction of space that things travel towards. And that's why it seems like there's an up and down from our perspectives. But the same can be said for time. There's something deeper that explains why we experience this direction of time just like we experience this direction on the Earth. And scientists think it lies in entropy. Thermodynamics says that systems have the tendency to travel towards a state of higher entropy. What is entropy? Well, all it means is a measure of disorder. For example, my desk is quite orderly. It's very hard to make it more orderly. But it's easy to knock things off the table, knock off my computer, knock off books, knock off pencils and papers. It's way easier to make it disorderly. There are way more ways to make my desk more disorderly than there are ways to make it orderly. That's what entropy means. This is how systems tend to operate in our universe. And this is pretty intuitive to us. If I showed you a cup of coffee that was this tan, homogeneous liquid, you would know that somebody once had cream in that coffee and mixed it together. That would be the intuitive thing to say, and you would never think that once it was mixed together that it could just disassociate and separate again back into cream and coffee. No, of course, you would think that the typical state of affairs is that that was a result of mixing, and it's not going to demix. So scientists think that entropy plays an integral part in why we have the sense of time moving in one direction towards higher entropy. So if the entire universe is moving towards a state of higher entropy, we could expect that there was lower entropy in the past. And what was that event? Oh, that's right, the Big Bang. The Big Bang was a very highly ordered state, and since then it has expanded. The universe expanded and gave rise to the disorder we see today. So the Big Bang is really the driver as to why we experience the flow of time that we do today. It has to do with the Big Bang itself. Just like gravity gives us this sense of direction in space, the Big Bang gives us the sense of direction through time. And another aspect of this is that our brains make sense of the universe through this ticking of time. We have a circadian rhythm, which dictates how we sleep and how we wake up, and that gives us a sense of when to do things. We also have memories of the past, and that gives us a sense of the flow of time as well. We don't have memories of the future, we have memories of the past. So that gives us a sense that time is flowing as well, and we're projecting into the future. So we constantly in our brains have this sense of time from the past and the future. And interestingly, many other animals have the same thing. In fact, the different types of brains of different animals gives rise to different notions of how fast this time is flowing. Interestingly, there's something called flicker fusion frequency, and in humans, it's about 60 hertz. In other words, our brains can process about 60 visual stimuli per second. In many other animals, for example turtles, it's around 15 to 30 visual stimuli per second. So from a turtle's perspective, they would see us moving faster through time because they perceive things more slowly. But to a housefly, their brains process information at 200 frames per second. So they would see us as sluggish. They would see us as slow. So the flow of time is also integral to our brains and how our brains are structured. So much like when you're watching a movie or on a projector screen, much like the projector is spitting out frames per second, that's what gives the sense of the flow of the movie. Our brains are kind of like the projectors, giving us these snapshots, making it seem like there's this flow of time. But we still don't have the full picture of time. We know that relativity isn't the full picture of the universe. There's something deeper, even. And that's quantum mechanics. We now know that superposition is a real phenomenon that happens in the universe, and entanglement is a real phenomenon. We can measure quantum states. How does quantum mechanics fit in our sense of this flow of time? Well, it's possible that you can fit the block model in a superposition in quantum mechanics where all states exist simultaneously. But the entanglement between us and other states is what we would perceive as the flow of time. This is complete speculation. But it's amazing to think that there's a quantum mechanical reason as to why we experience this flow of time, and it's not actually integral to the universe. It's an emergent phenomenon. In other words, one of the most human things we can think of in the universe, time, so familiar to us, is actually one of the most strange and mysterious things in the universe. The true nature of time is still a grand mystery, and how it fits into different models is not completely understood yet. Time after time, pun intended, the universe defies our intuitions about it. Surprise after surprise greets us when we poke the universe, when we learn about the universe around us. And although time is one of those things that we still don't quite understand, all we do understand is our small moment in this time. We are experiencing each other in this mere moment, this mere snapshot, this mere glimpse of what else is out there, this grand expanse. Let's cherish this time. It's the only time we may ever get.